In this video, we're going to begin what in our textbook is chapter 9, but it's a mechanics and materials textbook chapter on axial loading. So what we've done so far in this class is we've covered all the topics of statics and how to find forces on things, and then we moved into finding internal loads, defining stress and strain and material properties, and now we're going to start looking in depth at one particular kind of loading, and this is axial loading. And before we jump into it, there's this principle that I want to make you guys aware of so that you'll start to understand a little bit of why we make some assumptions in using the equations that follow. And this principle is called Saint-Venant. Sorry, it's French again. Saint-Venant's principle. A couple of French names so far in this class. So what Saint-Venant's principle says is really, it's not so much a quantitative principle, it's more of a qualitative principle. The idea is, let me draw a picture here. If I have a bar and I pull on it, and I go and cut it open and I look at the distributed loading inside the part. So let's say I apply a point load P to a long axial member, and I go and I take slices really close, a little farther away, even farther away. And what's going to happen is if I slice it open right here really close, what you'll notice about the stress distribution is it will not be uniform. It's going to be 0 on the edge and increase somehow and then go back down. So you remember how we would calculate an average stress value of P over A? That's not going to be a very good estimate of our stress when we're really close to the point load. Well, what if I take that red slice instead? So we're a little bit farther away, and guess what happens? It's going to be a little bit more evened out. So our extreme values won't be as extreme, but it's still not going to be completely uniform. Well, what Saint-Venant's principle says is that if I go far enough away from the end, eventually the stress across there will be uniform. And that stress is going to be P over A. The normal stress we've been calculating for a couple of weeks now in class. So this is the principle of Saint-Venant. It says that edge effects, these end effects, by end effects, what we mean is the fact that our stress is not uniform when we're really close to point loads at the end. Saint-Venant says that when we move away from the end, those effects go away. So what we do assumption-wise is we conclude that when we're dealing with bars that are long and slender, we assume that we can just treat the stress as uniform, because what we're saying is we're assuming that we can neglect end effects, neglect the fact that it is a point load. We're neglecting end effects, we're neglecting point load effects, and it's only good if we have a relatively long and slender bar. How long is long enough? How slender is slender enough? We usually want it to be at least maybe 10 times longer than the diameter is a good rule of thumb. But again, since Saint-Venant's principle isn't really quantitative, it's more qualitative, this rule of thumb is kind of just an approximate rule of thumb, is maybe 10 times longer than it is wide. And we are going to see Saint-Venant's principle come up over and over in this, what comes up in our book, because we have a lot of loads that are point loads. We want to look at their overall net effect on the structure, and that's easier to do if we make some assumptions like that the stress is uniform. So we're going to use that now to come up with a really helpful equation for dealing with axially loaded members. So let me draw an axially loaded member. The axially loaded member looks like this. It is long and slender, typically with a constant cross section. That cross section has an area A. It has a material modulus E, Remember, once I say it has a material property E, a Young's modulus E, that means we are in the linear elastic range and not ever leaving it. What makes it axially loaded? Well, we now need to apply some forces. So let's apply a pair of forces P on each end in opposite directions. And if this axially loaded member had a length L, which again better be a whole lot bigger than the diameter, what's going to happen due to that applied load P is two things. This axially loaded member, this long cylinder or pipe or rod or rope or wire, is going to get pulled, and because of that pulling, it's going to get longer. And we can either draw the longer on both ends or one end. I'm just going to draw it over here on this end, as here is our new length, and that new length is going to be the original length plus some change in length delta. We're going to use lowercase Greek letters delta. And here is the idea. We want an equation for delta. So we have a force P. That leads to a stress, normal stress sigma, P over area. Because I know my material property, from that I can get strain, epsilon. And from the definition of strain, I ought to be able to get delta. It's the change in length. So what are our equations? We know that stress is Young's modulus times strain. We know stress can also be written as force over area, and we know strain can be written as change in length, delta, over original length, L. Well, why don't we put it all together and get one equation for delta? So we're solving for delta. We put this all together. Rearranging, we would have delta is equal to strain times length, but strain is stress divided by Young's modulus. We still got times length, and let's replace stress with P over A. So we end up with PL over AE, or EA, however you want to write it. That, just using our equations and assuming what? That it's long and slender, so the stress is uniform everywhere, we're able to figure out the total length change of a bar of constant material, constant cross-section, and constant load that is length L, and there is our equation right there. Will the units work out with this equation? Well, let's see. Force is, let's check out units. Force is units of newtons. Length is units of meters. Area is units of meters squared. And Young's modulus is Pascal, so newtons per square meter. The square meters cancel, the newtons cancel, and I'm going to get units of meters, and deflection should be units of meters. So that's a very helpful equation. We can use it to find the change in length of all kinds of things. Well, what if the situation were more complex? We're not going to solve a lot of more complex things, but what if the situation were more complex? More complex. Let me draw more complex. One version of more complex. What if instead of a uniform cylinder, we had something that changes width? And what if we had a force that changed with position? So maybe a P1 over here and a P2 over here with a distributed loading along the length. So something is causing an additional distributed load. And we still have a regular old length L, but can you see how our cross-sectional area is going to change with position? Well, here's how we would handle this. We would do, what do we do whenever things are more complicated? We're going to make a delta X right there, which we're going to put up a coordinate system and say this is at location X. And what we would want to do is figure out the internal load at the cut through point X. We want to figure out the force there, the internal load, the area there, and everything else. And what would we end up with? Well, we would get, we might take a small section. Cut it open just a little bit. We would have P of X on the left and P of X on the right. We'd assume it's so small that the force is the same on both sides. We would have delta X is our width. And then we would have a small d delta X. right? I think I used, what did I use for change in length before? I think I used red. So this would get just a little bit bigger due to the applied load. So we would call this a little delta, I guess. And how would we then figure this out? We would say that our stress this time is going to be force, which depends on X, divided by area, which depends on X. We would say that strain is our delta divided by length, delta X. So instead of a delta over length is a delta over delta X. And then we're assuming just a constant material, sigma equals E epsilon. So how do we group this all together? We replace sigma with P of X times A of X, and we get P of X over A of X, sorry, I said P of X times A of X, is equal to E times delta over delta X. Let's bring the delta X to the other side and the E to the other side. We get delta is 1 over E, P of X over A of X, delta X, and then guess what we're going to do? Take the limit as delta X goes to 0, our favorite calculus trip, and add it all up. Add up from X, add up, how do I write that? Add it up from X equals 0 to X equals L. This is going to be an integral. Delta is going to be the integral from X equals 0 to X equals L of 1 over E times P of X over A of X dx. And so now we can have variations in load along the length, variations of area along the length. Young's modulus could vary along the length, but it probably doesn't. So we can pull that out of the integral. And now we can integrate to figure out the total amount of length change of the entire bar. So oftentimes P and A are going to be constant. You pull that out in front, integral from 0 to L dx is just L. Now, we don't actually do this integral very often. What's much more common is to have a situation where it's actually constant area, but maybe at some point the width suddenly changes. And maybe we have a P1 over here, and then suddenly we have a P2 right there, and then a P3 over here at the end. So what we'll do is we'll use the concept of integrating, except instead of integrating over little tiny delta x's, we're just going to add up, right? An integral is a sum of an infinite number of things. So instead, we're going to sum a finite number of things. And we're going to think about breaking our part up into chunks where the internal load is constant. So I'd have a blue section over here, and then maybe a red section right there. And then we'll say maybe finally a green section right here. And in each of those sections, area is constant and P is constant. So to solve for the total deflection, I would do the sum of the PLs over AEs, which in this case would be PL over AE for the blue section, plus PL over AE for the red section, plus PL over AE for the green section. So these are three simple calculations. We need to find the length of each section. That should be given in the problem. The area should also be given. We might have a diameter or a width and a height. The Young's modulus, we could have different materials here. So the idea being that we need to break this up into a section every time we change material, every time we change area, and every time we change internal load. The hardest part of this for students is typically figuring out what to use for P. And I want to refer you back to the beginning of a couple of chapters ago where we were finding internal loads. What we want to do is for that blue area, that blue bar, we want to cut it open inside the blue section and figure out the internal load using a little free body diagram. Then we'd want to cut open the red section, keep either everything to the left or everything to the right, draw a free body diagram to find the internal load. And then finally, for the green section, we would cut it open here. And most likely, all of those forces may be different. Some of them may be the same. We need to make sure we're using internal force. And then let me remind you of sign conventions. We've seen this sign convention before, But it does matter because what if some of these parts are in tension and some are in compression? Well, when we go to sum them up, we want to make sure we're adding the ones that are getting longer and subtracting the ones that are getting shorter. So the sign convention is that elongation is positive and contraction is negative. Let me draw a really quick picture. So if I had a bar and it gets longer because it had a force acting to the right, we're going to call that a positive force, and we are going to call that a positive deflection. On the other hand, if I had a contraction, that would be this direction, we would call that a negative deflection, and it would be caused by a compressive force, a negative P. So there's our sign convention: tension positive, compression negative. Shouldn't come as any surprise with the sign conventions we used for internal normal forces earlier in the class. Let's jump in with an example. Start simple and get more complex. First example is a thin wire. That's kind of a thick wire. It has got a 300 Newton force applied to each end. The length is 200 millimeters. And we are told that the diameter is 15 millimeters. And this little cylinder is made of a plastic material with a Young's modulus of 2.7 gigapascals. And we are supposed to find the change in length. Okay, so we start pretty simple, so let's start really simple. I can cut this open and draw a free body diagram if I want, but since there are no other loads on it, it is simply being pulled 300 newtons in tension. The force P is just going to be 300 newtons, and it'll be a positive because it's in tension. The length is 200 millimeters. I'm going to write that as 0.2 meters. The area would be pi times the radius squared. The radius will be 0.015 meters divided by 2, quantity squared. And then Young's modulus we're given is the 2.7 gigapascals. That's times 10 to the 9th newtons per square meter. Let's put it all together. Delta is 300 newtons is PL. Let me write it down. PL over AE. So what's that equal to? 300 newtons positive times 0.2 meters length divided by that area, pi times 0.015 meters over 2 squared times 2.7 times 10 to the 9th newtons per meter squared. And double checking that our units all cancel out. Newtons cancel newtons, meter squared cancels meter squared. So my answer will be in meters. And this comes out to be 1.257 times 10 to the minus 4th meters, or if you prefer to write it in millimeters, is 0.12. Let's round it to 3 significant figures. 6 millimeters is the answer. And that is much smaller than our 200 millimeter length. So that's a good sign because we should be dealing with small strains, small deflections. So there's the easy warm-up example. Let's do one that's more complex. Example 2. All right, this one we've got some kind of a shaft with a wheel on it, then another wheel on it a little bit farther down. And that's the end. It's just got the 2 wheels. Let's draw all of our forces on there. It has 2.0 kips to the left. Then here at this first wheel, it's got a pair of 3.5 kip forces to the right. At the next wheel, it's got a pair of 1.75 kip forces to the left. And then finally at the end, it's got a 1.5 kip force to the left. The letters here, they call this A, B, C, and D. And we need some dimensions. The distance from A to B is 18 inches. The distance from B to C is 12 inches. And the distance from C to D is 16 inches. Now we need the material and the diameter, or we actually are just given the areas here for each of those segments. So section AB is made of aluminum with a Young's modulus of 10 times 10 to the third KSI, and it has a cross-sectional area of 0.09 inches squared. BC is made of copper, so its Young's modulus is 18 times 10 to the third KSI, and its area we're given is 0.12 inches squared. And finally, CD is made of steel, whose modulus is 29 times 10 to the third KSI, and its area is 0.06 inches squared. And guess what we're asked? We are asked to find, let me put it up here, find the displacement from A to D. So the total length change. Okay, for every single, so we have 3 segments. Maybe we'll shade them in. We got a pink segment here from A to B, blue segment here from B to C, and a green segment here from C to D. And we need to find PL over AE, the deflection of each of those. I know the areas, I know the Young's modulus, and I can find the lengths very quickly from the picture. The one thing that I don't know are the internal forces. So I like to use free body diagrams to find these. So let's do a free body diagram of AB. I'm cutting it in between A and B. So it's a free body diagram to find the internal force in number AB, to be specific. So I'm going to cut it where I did that red dashed line, and I'm going to keep everything to the left because that looks pretty simple. And the only thing acting on it is that 2 kip force to the left. At my cut, I typically want to draw all of the possible unknowns. So a normal force, a shear force, and a bending moment. But if I sum forces in the y direction and some moments about the cut, I'll really quickly see that the shear and the V is 0, M is 0, but our normal force is going to come out to be, if I sum forces in the x, 2 kips. And it is, as I drew it, in tension, it's positive. So that section is going to be in tension. Let's next do a free body diagram of section BC. That's the blue section. So we want to cut right through it somewhere in the middle. You get a pick to keep either everything to the left or everything to the right. Doesn't make much difference for this problem. I'll keep maybe everything to the left. So everything to the left of the cut. What I have acting on it is 2 kips to the left on the end. And then I've got a pair of 3.5 kip forces to the right. And then I'll just draw my normal shear and bending moment, summing forces in the y direction, V is 0, summing forces in the moments about the cut, M is 0, I didn't even draw M on there. And summing forces in the x direction, let me write it down this time because we have a little bit more going on. I've got N plus 3.5 kips plus another 3.5 kips minus 2 kips. So I equals 0. So N is going to come out to be negative 5 kips. The negative means compression. Okay, then let's do the free body diagram of number CD. What I'm doing is taking the green section, cutting right through it. and keeping either everything to the right or everything to the left. It looks a little simpler if I just keep everything to the right. And I've got to the left a 1.5 kip load there. And then at my cut, I draw an unknown normal force, positive intention. I draw my unknown bending moment and my unknown shear force. Summing force is in the Y, shear force is 0, summing moment's at the cut, bending moment is 0. Summing force is in the X. You'll notice that my normal force points to the left and my 1.5 kips points to the left. So I will get that the normal force is negative 1.5 kips. So the negatives in the blue section and the green section mean that those two sections are both in compression and they will be contracting. The positive in member AB, that normal force being positive 2 kips means that section is in tension and that section is getting longer. Now let's put it all together. To get the total length change from A to D, I need to do each section's PL. I need to, well, sum up all of the PLs over AEs. So I will do it by color. First, let's do section AB. That's going to be 2 kips. Its length is 18 inches. Its area is 0.09 inches squared, and its Young's modulus is 10 times 10 to the third kips per square inch. The blue one, that's going to have the force is -5 kips. The length, going back up to my diagram, I used 18 inches for the first section. This one is 12 inches now. So we'll draw in at 12 inches for the length. The area of this one is 0.12 square inches. And the Young's modulus is 18 times 10 to the third kips per square inch. And finally, I need my last part, which is -1.5 kips. The length of this one is 16 inches. You see that up there? 16 inches. And then I divide it by its area, 0.06 square inches, and its modulus, 29 times 10 to the third kips per square inch. And now it's just dropped in the calculator. It might be worth double checking that all of the units cancel out. You'll notice we've got kips on the top and bottom in every equation, inches squared, and 1 over inches squared in the bottom of each equation. So we'll be left with inches when we're done. And punching all this into my calculator, I got that delta is -0.00157 inches, which means altogether, this whole assembly got shorter. Let's look at one more problem, one more example for this video. It's a little bit more tricky, but it's the same principle. So what I have going on next is a bar or rod of some kind that we're going to say is rigid compared to the other things it's attached to. So over here on the left end, it is attached to a wire that's pinned at the top. Over here on the right end, it is attached to another wire that is pinned at the top. And then off center, it's got another wire down here. And at the bottom of it, there's some kind of a ring, and it is being pulled down on by a force of P equals 20 kilonewtons. And let's put some letters on here. We've got A and B for the wire on the left, C and D for the wire on the right, and E and F for the wire that's down below. Let's get some dimensions. The wire on the left is 2 meters long and has a cross-sectional area of 60 square millimeters. Wire on the right is also 2 meters long, and it has a cross-sectional area of 45 square millimeters. And finally, oh, a couple more dimensions. From A to E, we know this is off center, but by how much? That's half a meter. From E over to C is 0.75 meters. The length of the wire from E to F vertically is 1.5 meters. And the area of this wire is 75 square millimeters. Okay, last bit of information is we are told that all three of those wires are made of titanium with a modulus of elasticity of 350 gigapascals. And we are supposed to find the displacement of F. How far down is point F going to move? So it seems like there are a couple of steps to this problem, at least. We will probably need a free body diagram because while I know that the force in wire EF is going to be 20 kilonewtons because someone's pulling on point F with 20 kilonewtons, I don't know how big the force is going to be in the top two wires with the point E being off-centered. So I'll need to do a free body diagram of AEC in order to figure out the relative amount of force in AB and CD. That'll be a statics problem. We can do that first. Then, once we figure out the force in all three of the wires, we can figure out the length change of the individual wires, and then we will probably need a little bit of geometry to finish this up to figure out, well, points A and C are both going to move down, probably not by the same amount, but that means that AC might rotate a little bit. So we may need some geometry to figure out where E is going to end up. And then finally, we'll have the additional length change of wire EF. So let's take this one step at a time. Let's start with a free body diagram of member AC. It's got a downward force of 20 kilonewtons from the bottom wire, and it's got an upward force of in member AB and an upward force in member CD. We can sum moments about point A, for example, to figure these out. And I would end up, in doing that, I'll have FCD times 0.5 plus 0.75 looks like 1.25 meters away, minus 20 kilonewtons times 0.5 meters. And I get that FCD is 8 kilonewtons. Well, this math is very nice. And then I sum forces in the y direction. I'll have FAB plus FCD that we just figured out is 8 kilonewtons minus 20 kilonewtons equals 0. So FAB should be, I think, 12 kilonewtons. And this is great. Now we know all of the forces in all of our wires. So I think the next step that makes sense is to figure out the length change of each wire. This isn't too bad. They all have different areas, but they all have the same material. They have a couple of different lengths. So let's find the length change in each wire. So the length change in wire AB, our governing equation is PL over AE. So the force in wire AB is 12 kilonewtons. Let me write it as, well, let's write it as 12 kilonewtons for a minute, and then we'll do a units thing at the end. The length is 2 meters, I believe. Yeah, 2 meter length right there. And the area was 60 millimeters squared. It's nice when they give us that. And then Young's modulus was 350 gigapascals. So what's going to happen with our units? I need to do a little bit of work on the units. I know that there is one GPa in 10 to the 9th pascals. I know that actually Pascal is a Newton per square meter, if that's a little bit better. I want to get rid of my millimeters squared, so I've got 1,000 millimeters in every meter, but I need to square that to get rid of my millimeters squared. And then finally, I know that there are 1,000 newtons in every kilonewton. So kilonewtons cancel, millimeters squared cancel millimeters squared, gigapascals cancel gigapascals, and then this newton cancels that newton, and this meter squared cancels that meter squared, so we're left with meters when we're done. It's a little bit of unitness. The number that we come up with is 0.001143 meters. Same process for CD. It's PL over AE. The force in member CD is 8 kilonewtons. Its length is 2 meters. Its area is 45 millimeters squared. And it is also 350 gigapascals. Run that through the calculator and we get 0.001016 meters. And finally, the delta in member FE or EF, it's got 20 kilonewtons of force on it. It is shorter. It's 1.5 meters long and its area is 75. So length is 1.5 meters, area is 75 millimeters squared, and it's times 350 gigapascals. And that number should come out to be 0.00, oh, this is interesting, 1143 again, meters. It's exactly the same as the previous one. It has a bigger force, shorter length, bigger area, but all those changes actually happen to cancel each other exactly out. That's really funny. Okay, we found all three of those. We got the deflections of each of the members. Now let's look at some geometry. I want to sketch out my original shape, which look kind of like football goalposts, off-centered. So what's going to happen is AB is going to move down a certain amount, and CD is going to move down a certain amount. One of these is bigger. AB is 0011. CD is 0010. So AB is just a little bit longer. So it's going to end up with some rotation here. And the way that I'm going to do this is break it up into a rectangle and a triangle. So the whole distance here is delta CD. And then this little difference in the distance here, right? The whole distance over here would be delta AB. This little delta distance would be delta AB minus delta CD. And then we're going to use similar triangles here to figure out how far down delta E is going to be. You remember how to do similar triangles? Similar triangles say that this side is to this side as this side is to that side. So taking the red ones, we would have, here's our similar, well, let me do it black. Here is our similar triangles. I would have, for the red ones, I would have delta AB minus delta CD over the whole length, which was 1.25 meters, equals the little purple delta E that I'm trying to find. Well, this, I don't know what to call that guy. Delta E would ideally be this whole amount right here. That would be delta E. So this little piece here, let's call something different. Let's call it, I don't have any idea what to call it. Delta little, the little delta, okay? That's the side of the triangle. Couldn't think of a good name for it. Delta little. It is over this width right here, because you know it's a little bit smaller and it's a little bit less length. So that's a 0.75 meters, right? This was 0.75, this is 0.5. So the whole width was 1.25. So we can figure out what the delta little piece is. To figure out the total delta E, then this whole thing is going to be what we call delta E. Delta E is going to end up being delta CD plus that delta little, right? Because delta CD is how far this rectangle goes down. Then we have that additional triangle down below. Finally, then, we also have some additional length change from the length change for member EF. So I did a little bit of this math. Delta E ends up being, if I simplify this, delta CD plus delta little is 0.75 over 1.25 times delta AB minus delta CD. That number I actually calculated. That is 0.001092 meters. And for a quick sanity check, it should be somewhere between what we got for delta CD and what we got for delta AB. If it's not, we've made a mistake. Delta AB was 1143, delta CD was 1016, and here we got 1092. It is, in fact, in between AB and CD, which is encouraging. So we find delta E, and now then the total delta F is going to be delta E plus the length change of member EF that we found up above. You add those up and you get 0.00223 meters, which is 2.23 millimeters. And that is the last example we're going to do for today. So to sum up, the main equation for today was this axial deflection equation. Delta is equal to PL over AE. We sometimes write it as the sum of all the PLs over AEs. Make my sum a little bigger, which allows us to have step changes in area, material, and force. And the thing to remember when using these equations is that P must be the internal normal force.